Hello, everyone. My name is Benjamin Rakowski.
I'm Dan Twist.
And I'm Seth Beecher, and we are ME61, working with Whitcraft Corporation in Eastford, Connecticut to design, fabricate, and validate a right-size press. Our faculty advisor is Dr. Vito Marino, and our industry sponsors are John Simmons and Alan Roy, who are from the engineering department at Whitcraft. Whitcraft is an aerospace company in Eastford with many other locations in the United States. They are also a large proponent of lean manufacturing.
Our team was tasked with redesigning some tooling for the Whitcraft production line. On the left-hand side, you can see what they call a monument. It's their 60-ton horn press that stands 14 feet tall and takes up 36 square feet on the floor. It's used to shear a ring of Inconel 718, seen on the top right. This press is much too large for this application, so our team has been designing a press that will be only 6 square feet on the floor, stand no taller than 54 inches, is easy to set up and use, and is OSHA compliant. In order to do this, we utilize a 3P down selecting process where you start with 7 sketches, choose the best 3 of those, and then continue to make 3 cardboard models of those designs. When working with cardboard, it is much easier to identify and iterate on problems because you're working in the physical space, and from there you can go on to create CAD models for the final design.
So we have here 2 of our CAD models. The one on the right is our November 2019 version. After sitting down and consulting with our sponsors, we were able to determine that this was not a manufacturable design. So we then went back and had to make some changes. On the left here is our final May 2020 version. It fits all of our objectives with being an easy setup. It's portable via pallet jack. It's right size for the flow line. We have included some black polycarbonate paneling around the bottom half of the frame. And then we have also included some access doors on the sides and the front for easy maintenance. Up on top, you can see the clamping ring prototype that we have included. This is where the operator would put the ring of Inconel 718. It swivels up and down, so they would place the ring, swivel it down, lock it into the die set using the 2 green push buttons on the front there. It would actuate the hydraulic cylinder, shearing the ring, and then they would be able to swivel the ring back up, rotate it, and lock it down into the die set again, repeating this process to get the 3 cuts needed. So here we have a couple pictures of the 8020 that the frame is made of. It's aluminum T-slot. On the left, we have the uncut stock, and on the right, we have our working frame build.
For the analysis component of our project, we begin with the stress strain diagram for unhardened Inconel 718, shown in the figure on the left. The failure point for this material occurs at approximately 130 KSI, and to figure out how much force we need to actually cut this part, we begin with the shearing force equation shown in the figure on the right below the shear blade in the part. The industry standard for this is 0.6 times the ultimate strength of the material. We chose to go with 0.8 to be more conservative and guarantee a good cut. If we skip down to the force shear, that's simply the length of the cutting edge times the cross section times the force required to fail the material. This yields a shearing force required of 7,000 pounds. To test this, we ran a trial at Whitcraft with a testing rig that could not go less than 7.4 tons. The 7.4 tons sheared the part easily. The cutting speed did not affect the quality of the cut. Thus, we concluded that a 10-ton hydraulic cylinder would be more than adequate to produce a good part. The FEA component for our project began with the figure on the left with our original design, which, as Dan said earlier, was unmanufacturable due to the small radii and sharp corners. The maximum displacement was 7 thousandths at the top of the die shoe with an applied force of 10 tons. In the picture on the right, we see our new design, which is modeled after a catalog Danley die set. It consists of 4 C1050 steel rods positioned at the bottom and centers of the die shoes. This helps to distribute the load more evenly. And we can see that it has a maximum displacement of 5 thousandths, which is half of the 10 thousandths displacement allowed by our sponsor.
The project status as of April 24th, 2020, we have completed the design and stress analysis of the press and die set. We have ordered and received all of the hydraulic components and electrical components, as well as the 80/20 frame components. We have sent the schematics of the die set to the engineering department at Whitcraft to be ordered from Danley. We were unable to test the electrical or hydraulic systems or run any dry cycle testing on the press, or as well as we were unable to shear an actual part.
Thank you.
Thank
Thank
you.
you.